Introduction to bridges. Bridge. Bridge is the passage provided without blocking the way underneath. Bridge could be used to serve pedestrian, road for motor vehicles, or mixed traffic road, railway road. It's the passage which is provided over the obstacles which could be of nature, river, canal, valley, gorge. Here is the slide number 2 where we have the general cross section of the bridge illustrated in plan and elevation. Bridge structure can be divided into foundation and superstructure and substructure. Foundation comprises of piles and pile cap which lies beneath the bed. Substructure comprises of deck, girders, soffits, and superstructure comprises of bearings, pier cap, pier. The center line of the two structures, that is the bridge and the obstacle underneath, are at different levels, and the angle between the two center lines should not be less than 45. If we will allow the angle less than 45, it may result in the scouring of the bed and as well as of the backfill in the apartment. In slide 3, we can easily look at the profile of the riverbed, or it may be of the floodplain, defining the various regions, that is the upper bank, lower bank and the channel, and the water level at various levels, like we have extreme high water and normal high water. Normally a bridge, like for the design, when we design a bridge, it is to be designed for the highest flood level, and highest flood level, the data for highest flood level is gathered from 100-year flood, that is the peak flood that has ever occurred in 100 years. In any water course, we have three we have three stages of any water course. We have upper course, we have middle course, and we have lower course. Upper course, that is provided with very steep gradient, and the middle course is followed by shallow gradient, and the lower course goes relatively flatter gradient. Upper course is provided with boulder stage. When we talk about upper course, it is the boulder stage where the flow of the water is very high and the rushness of the water indicates the highness of the velocity. Middle course is provided with floodplains and the silt deposition at the edges, and the flatter course is much flatter. It may result in the very low velocity of the water, as we can see in the Jhelum. The various stages of the river with varying gradient at each level, what we gather from there is that it gives us the idea about the span of bridge and bed profile, hydraulic data, scoring, water levels, that is HFL, OFL, LWL, and also we understand that when we are providing a foundation, we have to understand that how much amount of scoring tendency the water in that very stage of the river has. If it is in the boulder stage, then we provide very concrete foundation, and because the bed itself is very strong. But if we are going for the lower stages of the river, we have to understand it's a silty base, and we have to provide the provisions for the scar depth and the grip length in any well foundation. So following provisions are dependent on the nature of the bed profile. So that is why when we design a bridge, we have to understand the study of the bed profile is very much necessary, and the stage of the understanding of the stage of the river is very much necessary. Here in slide 5, we are understanding some terminology of the bridge from the cross section of the road. For example, we have here at the edge, we have pedestrian gallery, we have road with nothing over it, simple road, and then at the center we have road and over which a bridge is provided. So when we see it at the central portion of this cross section, we see vehicles with double-decker buses, like they are the double-decker buses mounted on the road here. So it indicates something, that any road which has bridge over it has to be designed for the vehicle having maximum height. For example, we have cycle, we have scooter, we have car, we have trams, we have double-decker buses. So it has to be designed for the bus having, or the tram having, the highest height or the maximum height. Also, the soffit of the bridge has to be provided with a proper clearance with the top of the bus, so as to avoid any inconvenience in the movement of the traffic. Here in slide 7, we see a bridge passing through a river body and covering the obstruction, and we see a little rise in water level. So the rise in water level due to the obstruction in the waterway, it could be a channel, it could be a flood channel, or it could be irrigation channel, or it could be a simple river or drainage basin. So when we provide the bridge structure in the very drainage basin or any river structure, so there is a certain rise in water level, and that rise in water level is referred as efflux. And this efflux is seen maximum at the cross section of the river where the bridge structure is supposed to be, and it gradually decreases some distance ahead and beyond the bridge structure. Now, classification of bridges. The bridges can be easily classified in 3 simplest categories: bending, compression, tension. When we talk of bending, we provide beams in superstructure because that's what they are best to support. For compression, then we go for arches, and tension we go cable bridges. So first type of classification we have according to form or type of superstructure. Here we have slab bridges, we have beam bridges, we have truss bridges, arch bridges, and cable stayed or suspended bridges. Slab bridge is simple deck slab bridge that is provided from end to end, resting from one pier to another. Beams we provide I section or T section beams resting from one pedestal to other pedestal from one pier to another. And trusses are where we provide proper N type truss, Warren type truss, or Pratt type truss, or we have so many numerous classification of trusses. And we have then arch type bridges and cable stayed bridges, which goes best to resist compression and tension respectively. Based on the different type of material, the classification can be done. Like the material can vary from timber to concrete to stone to RCC to steel to composite bridge. Like where we have two materials amalgamated together. So the third type of classification is based on the length of the bridge. And the length plays a very significant role in classifying bridges. A different length can altogether make a bridge named different. For example, if we have length less than 6 meter, it's a culvert. And if we have length ranging from 6 to 60 meter, it's a minor bridge. And length exceeding 60 meter or greater than 60 meter makes it a major bridge. And if we have span of the bridge larger or greater than 120 meter, it makes it a long span bridge. And one more classification, maybe that we will take later. If we have span 1 meter bridge is called as causeway. So depending upon the different length of bridge, we classify bridge in a different manner. Now we have the classification here based on function, that is the purpose they serve or the function they have. So first classification here is the aqueduct bridge. Aqueduct is a hydraulic irrigation structure, and we have a classification and irrigation of the structures, that is aqueduct, super passage and level crossing, where the two structures meet at different levels. For example, in aqueduct we have canal over drainage, and we have super passage where we have drainage over canal, and level crossing where the two structures meet at the same point, and we operate manage and maintain the flow of water by gates or flow management simply. So aqueduct is something which is provided, a canal moves over the drainage structure, and this purpose of this function of it makes it a different bridge. Then we have viaduct, long bridges or series of bridges connected together across a valley or gorge or ravine we know it as a viaduct. Then we have pedestrian bridge. We have footbridges, could be steel footbridges or timber footbridges. In old city of Srinagar, we come across numerous footbridges that cover that moves across the small tributaries. And then we have highway bridge, which is used for the continuity of the highway. And we have road cum railway bridge. Road cum rail is something which is used by pedestrian as well as by the road, or we have or also known as pipeline bridge. Followed by the classification based on the interspan relationships. For here we have simply supported bridge, cantilever bridge, and continuous bridge. Simply supported is simply which will act as a simply supported beam, and the load will be taken as a simply supported mechanism. And we have cantilever and continuous. In cantilever bridge, we have a projection from each pair, that is continuous projection, and that acts as a cantilever portion, and that cantilever portion supports the slab. Example of the cantilever bridge is Amira Kadal bridge. It can be easily seen from the side view of the Amira Kadal bridge, that the central portion is the slab resting over the two cantilevers. And the continuous bridges, where the load is taken by the bridge structure in a as in we see in the form of the continuous beam. Then we have temporary bridge and permanent bridge. Temporary bridge and permanent bridge is simply the usage or the service they provide. For example, we have temporary bridges. They are usually military bridges. For example, they are mounted or erected easily and dismantled easily at the same time. We have pontoons are the temporary bridges. They are mounted, even they can bear the load of tanks. And then we have permanent bridges. Any RCC structure or any steel structure that is welded is a permanent structure. That's a permanent bridge structure. So this is the classification so far. So now we have foundation. In foundation, we have first spread foundation. So just like for any wall, we understand the spread footing foundation and we design with it proper footing. So is for the bridge. For any bridge which is subject to the very minimal load, very less load, we can go for the spread footing foundation. And now we have raft foundation. Raft foundation is to be provided for the soil with low bearing capacity, soil which contains air pocket or compressible air, where the stress distribution is less and where the surfaces are very much unpredictable. It is used for the short span bridges also, and as we provide the raft foundation, it is very much the susceptibility of the scouring is very much, erosion is very much, the piping action or the peeping down of the water molecules and taking the soil molecules near the adjacent to the raft out can result in the instability of the foundation. And to disallow such circumstances, we use cutoff wall. Cutoff wall is simply a wall that descends from the foundation of the raft and which breaks all the channels, which may result in pulling out of the soil molecule and unstable and making the surface unstable. So and the safety of the foundation is further enhanced by providing rubble aprons. The rubble aprons resist and bears all the thrust and impact of the water that is upstream as well as downstream to some extent. Followed by, now we have pile foundation. As and when to deal with long span bridges and heavy loading bridges, the set of piles are installed and these piles are covered with pile cap, providing the seat for pier. We have a video in all these slides. If it is if it will support, you can look here. If not, then you can easily go to the YouTube and check for the mounting of the piles and the pile cap. Now we have caisson foundation. Caisson foundation is simply when we go for providing a cutting edge over the surface of the bed of water after diverting the water by means of sheet piles or by means of the what we use to coffer dams. So when we provide coffer dams and sheet piles to divert water and provide the sufficient ample workspace, there what happens is that we get the over the bed of the surface we provide the cutting edge, and this cutting edge is properly attached with the shuttering, and in this shuttering we go for the pouring of concrete, and as and when the load increases it sinks and the extraction from the central muck is made from the clamshells, etc., or by manually it could be extracted. The central muck could be excavated manually. So after that the caissine sinks down, and we lift the shuttering up, and as and when we pour the concrete into it. The caissine foundation is very much susceptible to the tilting, and to avoid tilting we have you might have seen, if you have ever visited a bridge site, you might like ongoing construction bridge site, you might have seen that huge stacks and piles of large concrete cubes, and those cubes are only used to to rectify the tilting of the caisson foundation. For example, if the caisson goes on sinking, like there's a tilt, and the tilt has occurred because of the disproportion of the weight on the either sides of the caisson, that disproportionation the disproportionation can be proportionated by putting the weight on that side on which the sinking of the caisson is less. So this is so far what we had foundation. Moving on to the next slide. Now we are discussing here boring methods, and these boring methods are for the piles. First we go with the auger boring. Auger boring is simply why with the help of the auger we draw in the auger into the soil surface and bore up to the desired depth, mechanically or manually, till dia and desirable depth and dia are achieved, followed by direct mud circulation method. It is then it's an on-site method where with the help of the winching machine we lift and draw the hammer, and through the body of the hammer we pour in the slurry of water and bentonite. What is bentonite? Bentonite is rare earth. As bentonite as slurry hits the surface, the cavity of the pile, it draws out the muck from the cavity, creating the space for the pile. So till the desirable depth is achieved. Once the desired depth is achieved, we put in the cage in the cavity for which the pile cavity, and after we have put the cage in the pile cavity, now it is the time for concreting. So we, with the help of trummy pipe and the hopper, we pour in the concrete, covering the internal surface and the reinforcement also, till the surface of the NSL is reached, and beyond the NSL we cover the height of cutoff depth. Cutoff depth is something which is a depth that is otherwise also to be chiseled off or chipped off or mechanically taken away to reveal the reinforcement for further construction. But cutoff depth, why is it taken away, or why is it known as cutoff depth? Because this is the depth where the mud particles are accumulated with the slurry of the cement, or the slurry gets piled up at the upper surface, or it's mostly the cement slurry covering the area. So that is to be taken away, so that with the reinforcement may be revealed. After the reinforcement is revealed, it is drawn into the further structure. Pile cap, this reinforcement goes into the pile cap, and then the pile cap is drawn over it. So what is a trummy pipe which is used for pouring the concrete? It is simply 2 meter of pipes coupled together, provided with the hopper at the top. Once the concrete is filled, once the concrete goes on filling this cavity of the pile, the upper couples are loosened and the pipe is removed, and the hopper is joined back till the concreting is finished. So also what we have is that there is also the loss of mix in as we go for the concreting in direct mud circulation method, because as we put water of bentonite slurry into the pile cavity to for the excavation, for the extraction of the earth into the for the excavation of the earth, what happens is that there is water already present into that cavity, and when you pour the mix of M20 or whatever, so you pour the mix into the cavity, it loosens, like the concentration of the mix gets decreased. So what is recommended by codes, that you go for 10% higher mix. You already design the mix at the higher end, because you are aware of the fact that on site when you will do the concreting, it will lose its concentration, because there is water already present into it. The mix will dilute. So for that reason we have to go for the higher mixes at the design end, and then so that the desirable mix can be achieved at the construction site. Also, the water has to be properly drawn out from the site, because otherwise it may create clogging or not satisfactorily site conditions. So proper trenches to be excavated for that, and a proper direction is to be provided. A path is to be jolted down for the water, so that it could easily move in through that path. So now we have the third process, that is the reverse mud circulation method. In reverse mud circulation method, it is the most appropriate method than the direct mud circulation method, because direct mud circulation method makes the site conditions a little bit muddy or not so appealing, but reverse mud circulation method is very much better method than the direct mud circulation method, as in the water which is used for boring the method is same. The method of both of them is same, almost same, not exactly same but almost same, but here no bentonite is used. In reverse mud circulation, no bentonite is used. Simple water is used, like as a jet of water is used in to make the mud slurry and take the muck out of the pile cavity, and once it is done, the water is taken into the trench and it's allowed to still there, like proper steady state is given to the water there, and after the stillness of the water, the mud or the silt particle settles down, the water could be reused from the trench. So with the help of the vertical pump, the water is poured into the bore, and after it's poured, it draws out the muck from the cavity, and after achieving the desired depth and dia, we go for concreting after putting the reinforcement cage into the pile cavity. Now here at slide 30, we are seeing the cross section of the well foundation. We learned above that in the classification of foundation we have caisson foundation. Here you can easily understand what's the cross section or what the caisson foundation looks like. So here we can see cutting edge, well curb, and then the steining, the vertical erection of the concrete or the masonry or whatever so has been used as the material. And then we have the top plug, and we have sand filling, and then we have the bottom plug. Bottom plug is provided so as to disallow the further sinking of the structure once the desirable height is achieved. And then we have the intermediate plug also, which is not shown here in the cross section of the drawing, but we also have the intermediate plug also. What is intermediate plug provided for? It's another structural member of it with no significance. So what the significance here is nothing, but it is simply, for example, here we have the full on, like the whole of the internal cavity is covered with sand. So what the intermediate plug will do is, beyond between the bottom plug to the intermediate plug there will be nothing, but between the intermediate plug to top plug we'll fill it with the sand, so we have reduced the quantity of filling. So at the top of it we provide the RC slab, and then we have pier or abutment. It can serve the base for the pier as well as for the abutment. Now we have here in the same slide number 30, we have types of well shapes. It could be simple circular, dumbbell shape, rectangular well, double rectangular well, double octagonal well, double D well, twin circular well, depending upon the type of load, the type of structure, and of course the nature of the bridge. Now on slide number 33, we are seeing a 3D image of abutment. What are abutments? They are the end supports at the ends, mostly provided to support the lateral pressure at ends. So what an abutment does is it acts as the seat for the deck slab or plate girder or beams or arches or trusses or any of the structure what the bridge is made of, but it provides the seat for that structure as well as holds the approach road. It helps the approach road and the bridge to meet at the same level. So it is the structure of the abutment comprises of foundation, abutment vertical structure, now backfill and wing walls. What wing walls do? They help the abutment to hold the backfill. The earth behind the abutment is holded by the wing walls. So wing walls could be classified into straight wing walls, splayed wing walls, return wing walls. So they are shown, the photograph of each one of them is shown in the slides ahead. You can go and check there. And also there is one thing which is known as dirt wall. Dirt wall holds back the muck vertically, like exactly from the vertical structure of the abutment, it holds back the muck. So this is abutment, and it is provided at the ends of the bridge, at both ends of the bridge. On slide number 36, we are understanding piers. Here we have the cross section of the pier. A pier is an intermediate support in the bridge structure. It supports the deck slab of the two spans. It's a resting place of the deck slab of the two spans, and it carries the load in a simply supported manner, in a cantilever manner, or in a continuous manner. And either in all of the manners, it acts as the intermediate support of the deck slab, beam, truss, timber beam, timber truss bridge, or whatever we have here. So the cross section of the pier is very much typical and different, which makes it as a different member than that of the abutment. Though the one of the characteristic of the abutment and the pier is same, that it holds the upper structure, but what makes it different is, first thing, it's an intermediate support, and second, it faces the impact, the thrust, and the whirlpools you can see are made around the cross section of the pier. The cross section of the pier is very much typical. It is usually provided with a cutting edge towards the upstream, so as the water approaching to the structure may be easily diverted on the along the peripheries of the pier. So there's a proper angle to that, and that is either with a proper cutting edge or with a beveled edge. So that is one thing, and that type of structure has peculiarity also, so as to avoid the formation of the whirlpools at the pier or at the central portion, so that the water may not like form vortexes there. So pier has its own significance and own and its design its own way, understanding the susceptibility or the vulnerability of the cross section there, and the susceptibility of forming of the whirlpool, vortexes, efflux, and etc. Bearings. On slide number 41, we are seeing here in picture bearings and the cross section or the internal cross section of the bearing. Here in the picture we get the idea that where the bearing is almost an idea the where the bearing is to be placed. So it is a key structure that is to be provided above the substructure and beneath the superstructure. So it is simply a link between the two, where maybe also a mode of transference of the load or the moment, or any sort of stress. So bearing has its very important significance in the structure. It acts as the seat for the beam or for the slab over the pier or an abutment, to take all the bending, to take all the moments, to take all the stresses, or any sort of creep from or displacement from the substructure, and maintain the stability of the structure. Bearing is simply provided in the bridge in numerous ways and forms depending upon the design. We have pin and point type of bearing, where one end is pinned and another end is left free, so that the proper thermal contraction and expansions may take place, so that the bridge is having free release of the moments. The moments could be easily released. And also we have rocker roller, and once a person may go through the book, one can understand the different types of bearings that are used in bridges. So bearing has its very important significance. Here we are seeing a neoprene bearing. It is the sheets of iron plates embedded in the pads of neoprene. The pad of neoprene, what it does is it damps the whatever impact or the resonance is created in the bridge, and it helps the bridge to stay strong and serve its strategic importance, or serve its stability. So any bearing that is which is provided, it is provided to avoid the development of the stresses due to temperature or due to deflection. Also it is provided to avoid the chances of creep, chances of shrink, the creep that is of its natural form, or that occurs due to the material that is used, that is the shrinkage of the concrete. Also thermal expansion and contraction, and also the settlement of the supports in any case. For example, maybe the bed, maybe like inappropriate construction in foundation or whatever, so may be the reason. So neoprene or any type of bearing is provided so as to help the bridge structure to stand still and to support the load. Now here we are understanding joints, and first of the joint we have is construction joint. See, it's impossible to achieve the continuity in the construction. So whenever there is a break in concreting, we end the concreting with construction joints, so that very much next day the continuity may be achieved. In the next slide you can see the construction joint. Now we have expansion joint. Expansion joint is something which is, but one may walk on the bridge and may notice a strap of metal on the bridge structure and wonder what is it. It is nothing but beneath that strap of metal lies a proper gap between the two deck slabs, and that gap is actually the gap for expansion. If the expansion stresses may lead to the expansion of the slab, that gap is provided for that. The periphery of each slab is covered with a strap of metal whose teeth are embedded into the concrete of the deck slab, so that the gap of proper specified distance or centimeters or mm's or is maintained, and that is covered with a metal strap. Because metal strap is why we cover the expansion gap with metal strap. You have to go for the macadamization of the bridge road, and what will take the macadam? It will not stand on nothing. So we cover that strap, we cover that cavity with the metal strap. So if one is driving on the bridge road, one may drive and suddenly receive a bump, like thoda sa lift ho jati hai gaadi, but then one is like, what is it? It's actually the place you have just moved over the expansion gap. Second thing is contraction joint. Contraction joint is usually in the slab, so it is provided with the help of the dowel bars or the longitudinal bars that are properly assigned in a longitudinal direction or transverse direction. What happens with them is that if the contraction occurs, they still hold the two slabs together. Now on slide number 49, we are seeing some workers working on bridge deck slab and laying some black material over the surface. So technically we call it paving of bridge. So this paving of bridge is simply when we cannot allow the bridge for vehicles to move simply directly, though it's a rigid surface. A vehicle can move over it, but it should not be allowed. It may result in high wear and tear. Plus, the surface of the bridge is like it has projecting nails, reinforcement projecting out from some places. So this place needs the surface of the concrete, the deck slab needs to be cleaned. It needs to be make dust free. It needs to be washed, and the nails and the projecting reinforcement needs to be cut off. And once it's done, it's open for the use of for laying of the seal layer, the seal coat. What does seal coat do is that it seals every fissure, every crack, or every shrinkage that has ever occurred, or pore that is on the deck slab, so that the paving process can be carried out. Paving of the bridge is done so as to ensure the uniformity of the overall road structure. That is, the approach road should not be different from that of the road. The color, the nature, the smoothness should be same. Also, then for once the seal layer is laid, we provide the mastic asphalt. We heat the mastic asphalt on site, and we allow it to flow over the surface, and then properly layer it, the entire deck slab with it, followed by wearing course. So what we have is, with the sub base and base course, we have DLC and PQC. We have dry lean concrete, and we have pavement quality concrete. Pavement quality concrete for this one is M40. What happens is that beneath the DLC we go for we have to clean it, and we have to provide the pavement quality concrete, and that is to be provided with the contraction joints and all. So this is the paving of the road of the bridge slab. Once it's paved, it's properly provided with pavement quality concrete, or it's properly bitumenized, it's macadamized, so it could be used for traffic. On slide number 50, we are understanding appurtenances. Appurtenances are simply the secondary structures which are provided on the bridge, and first one of them is handrail. Handrails are provided on the either side or on the single side of the bridge. Actually, on the both sides of the bridge, basically, if it's not provided with a median. Then handrail is actually defines and totally shows the usable area or the paved portion of the bridge. Now we have footpath. Footpath is is something which is used by pedestrian, which is of pedestrian use, and of maybe used by cycles also. So sometimes, then we have it's actually 1.5 meter projecting cantilever portion on both sides of the bridge, used by pedestrians. So footpaths also have the application, the use of carrying out ducts, like the tubes or ducts that carry telecommunication cables, telecommunication cables, we have electricity wires, and then so many other things. So one has to take approval from the public works department, the one which owns the bridge, so to let the cable be supported into the duct of the footpath. So third one is the drainage. So drainage is something like we like in highway we have a whole chapter over drainage of the roads, because it's considered to be a very vital portion, because if you will not divert or take away the water from the surface of the pavement, it will deteriorate the pavement. So same is the case of the bridge. So bridge is nothing, bridge has no less significance of drainage than that of the road. So drainage here is also very important. So while we provide the pavement or the macadamization of the bridge surface, the camber is maintained, the camber is ensured that it is present so as to divert the water. So proper cavities or galleries are provided into the deck slab of the bridge so as to divert the water way off the surface of the bridge into the obstruction below, into the river channel or flood basin or whatever it is passing over. Then it is either taken in the pipes or ducts, or it's directly taken down into the surface. What one can easily, like I can make quote here an example. If one may walk over the footbridge, there are numerous like cavities or the holes provided at the edge or the periphery of the bridge on the either side, and one may notice that what is it, and it is like it is actually for the drainage purpose. It is actually to divert, and you can slightly, there's a very slight slope, very mild slope provided on the surface of the footbridge, and it's for every bridge. Like you will easily see a proper hole into the footpath or on the deck slab surface, which takes away the water down. Then we have the approach slab. Approach slab is something which is very important structure in the bridge, though secondary but important. What is its significance? What is its importance? It is actually the slab which connects the actual road to the bridge. There is limiting gradient is basically that governs the gradient of the approach slab. It's very flat, no matter whatever be the gradient of that of the actual road. The limiting gradient is it shallows down, like it's a milder slope that goes that allows the access to the bridge. So it rests over the backfill. It is totally guarded by the wing walls of the abutment. It has same specifications as that of the existing road. It has same specifications as that of the bridge, and so it is an intermediate stretch of road that is of utmost significance, that connects the existing road to that of the main bridge. Like it's very much analogous, no? And it's very much analogous if we will say that we have straight line, and then we have the curve, and then in between the straight line and the curve we have the transition curve. So it is very much like that. It connects the two. It has a variation in gradient. It is as I said, that limiting gradient is the gradient that governs the approach slab. It's very mild. It helps the vehicle to move from the design speed of the road to the speed of the bridge. So that is how it makes the transition of the speed.